Okay, so I've made the notes for the first 3 days the exact same. The exact same between -1 and -2. There's extra stuff for the -1s, obviously. So on the bottom there, I've just made it generic because I think everybody gets Math 20-1 functions. But really, this is just, of all the functions that we do, the -2s are just going to do quadratics. Does that make sense? Essentially, functions are graphs. So I want to start off by doing a bit of a review of graphs you guys have done before. If I were to give you guys an axis like this, you guys familiar with that?
Yeah.
Which one's the x-axis? The horizontal is x, which means the y-axis is up and down. If I were to ask you to plot the point 3, -2, you guys know where to plot that?
Yeah.
3 over 2 down, it would be something like there. 1, 2, 3 over 1, 2 down, something like that. If it makes a graph, it's a function. And for the most part, you guys should have learned about one type of function, a good old straight line graph. Okay? Over the next, however long you take math, we're going to learn about more functions. In -1, we're going to learn about what's called a quadratic function, which has kind of a U shape to it. -2, we learn about those as well. The -1s will also learn about an absolute value function, which looks like a V. We're also going to learn about a reciprocal function. Some of you guys in physics might recognize where it kind of goes down like that. And then eventually we're going to learn so many more. We'll learn about exponential functions. We'll learn about logarithmic functions. We'll learn about sinusoidal functions. All of the ones I just said, -2s actually learn as well in the grade 12 course. So this is kind of a really important opening unit because you just learn them at different times. The -1s learn some of them now, some of them next year. The -2s learn only quadratics now, and the rest of them in grade 12. That's the way they broke up grade 12. So, long story short, you need a graphing calculator. If you don't have a graphing calculator, you're kind of screwed. Because you really, really, really need one in order to be able to do a lot of the graphing. You can do it by hand, but like beg, barter, borrow, steal, ask Nomi whether she'll rent you one, but you need a graphing calculator. Okay? Okay, so today what I want to do is just review. Today should hopefully be talking about a lot of vocabulary, a lot of terminology, and I want to refresh on how you use your calculators, because Quan should have showed you this stuff last year, so hopefully this is not brand new information. So we'll see where we're at. First definition. A function is a relationship. A function is basically how one variable relates to the next. Often it's in a graphical or an equational form. Let me give you an example. Y equals 2x. That's an equation. And at some point you guys should have learned how to put that equation into your graphing calculator and make a graph out of it. Because the relationship is whatever x is, y is double that. If I give you an input value of 1 for x, your y value would be 2. If I give you an input value of 3, your y value would be 6, right? Because all you're doing is you're doubling. Right? Essentially, you need to know relationships. Are you doubling, maybe doubling and adding a number? This unit here, we're going to talk about how to square values. But I'm really going to hit on this concept here of like a machine. I want you to think of inputting a number into your function and getting back out an output value. So let me do another example here. Y equals 3x minus 4. Think of this as a machine. If I give you x is 0 as an input, if I plug in 0, what would y be? -4. Here's y. 3 times 0, 0, minus 4. Okay. If you plug in a 0, it gives you -4. And essentially what we've learned how to do is start putting these things in like an XY table of values. We'd say, well, 0 gives you -4. And then we move on to the next number, and we say, well, what would 1 give you? And do it again, okay. 3 times 1, 3. Minus 4, -1. You keep going. 2, 3 times 2 would give you 6. Minus 4 would give you 2.
It's pretty easy.
Right. You guys have done something like this before where you graph? Right? And then the idea would be is that these are ordered pairs on a graph. So on a graph, you'd say that 0 goes with -4, 1 goes with -1, 2 goes with 2, 3 goes with whatever 3 goes with, and eventually you would have learned how to make some sort of graph like this. Is that familiar? What I want to do then is just make sure you're familiar with the vocabulary we're going to use. So I'm often going to use the word input. Well, input is x. Whatever your x value is, it's an input. And output is y. But sometimes we write this in a different notation. We write it as f bracket x. Have you guys ever seen that before, f bracket x? Yeah. Or any letter, right? Essentially what it means is that x is the letter that we're using the equation for. If we wrote the equation y equals 3 star plus 1, you could write it as f bracket star, because star is your variable. Whatever variable you have, that's what goes in the brackets. Do you guys know these words, domain and range? Yeah. Okay. Domain basically refers to, well, what x values do you have? And range refers to what y values do you have. A lot of times, you guys might have done something like this. X is an element of the reals. Is that something familiar? I'm getting some nods here. Okay. Most of your beginning level functions, that's true. But as we get further and further into functions, either in the -1 or -2 course, eventually we'll learn that that's not always true. X is not always every value possible. So I will cover that as we need to get to it. So, long story short, functions are basically an equation. If you have an equation, it's a function. So what I'd like to do here is just a basic activity. Let's try making some equations for area of a circle as a function of its radius. Do you guys remember this from junior high math, the formula for area of a circle? Pi r squared, yeah. There we go. Now here's how you'd write this in the proper notation. You would say area equals pi r squared. But we like to write it in function notation. We put something in a little bracket right here. We'd say that area is based on what variable? Since the variable r. You're getting it. There's only 23 letters left, but yes. Does that make sense? The idea being that because r is our variable, we put an r in brackets. But there's another way we could have written this formula. I'm just going to write it out. We'll see whether you guys can pick up on how I pulled this up. Okay, you guys know what a diameter, right? Yeah. The diameter isn't, if you cut diameter in half, it's not a radius? Yeah. Right? So isn't diameter over 2 this radius right here? Yeah. Well, then since d is my letter, it goes right there. That's all. That's all the notation means. Essentially, in a way, this is your x value, and this is your y value. For you guys in my physics class, we already started doing this with that last lab we did there, where then I'm going to ask you to start plotting a y value versus an x value and get some sort of graph. Let's try another one here. Let's do the equation for the volume of a cube as a function of its side length. So first I'm just going to draw a picture of a cube. Let's say the side length is x. That means this is x, and that's x. What's the volume then? How do you find the volume of something like that? Length times height. That's all it is. Length times width times height. Well, the length is x. The width is, well, it's a cube, right? So the width is also x. The height is also x. So the volume of the cube would be x cubed. But that's not the notation we would use, though. We would write it like this. Volume based on an x value is x cubed. That's all. It's a subtle little twist. But it does kind of make sense going forward that this just lets you know what variable we're talking about. I'm actually going to skip this last one here because none of you guys have done chemistry with me yet. And so you probably don't know how to convert Celsius to Kelvin. So maybe I'll just leave that one for right now. But does this make sense, the idea of just putting a little variable in brackets? And it just lets you know what variable we're talking about. Most of the time for us, we're going to do a function based on x's. And so therefore the variables we have are x's. If we make it a function based on smiley faces, well then it's just a smiley face. That's all. What if I said that it was f bracket 2? You guys ever seen this before? No. Well, here, look. If this was x plus 3, but now if I change this to a smiley face, it becomes smiley face plus 3.
2 plus 3.
Well, then it would be 2 plus 3. Well, now in this case here, it's not an unknown value. 2 plus 3 is actually now 5. And you guys already actually know this. Maybe you didn't realize you know this, but this is a point. This is the point 2, 5. If you plug in an x value, you get out a y value, and that's a point that you can actually plot on a graph. So my goal today is to try to help bring all of this stuff kind of full circle and just work on all the terminology first, work on the base level skills, especially if you haven't seen this before. Okay, I do want to talk a bit about domains. Domains are essentially your x values. Here's 2 words I want you to know, discrete and continuous. I think you probably heard them before, but in case you haven't, discrete data is data where it logically can only be like 1, 2, 3, 4. 2.5, not logical. For example, if you ask me how many children I have,
2.5.
I have 2. It's not really possible for me to have 2.314 of a kid. You know what I mean? Like you either have 1 or you don't. Right? Discrete data then is usually in whole number increments. You know what I'm saying? Whereas continuous data is something where could you have a partial of something? And if I asked you how many, I don't know, how tall you are, you don't have to be just 6'1". You could be 6'1 1/4. You could be 6'1 and 13/75. Right? You can always find like smaller increments. So if it's possible to have small in-between increments, it's continuous. Otherwise, it's discrete. Here's why this matters. Okay. When you're plotting a graph, if it's the sort of thing where you can only have 1 or 2 or 3 or 4, and you plot data like this, like if I asked you what your, I don't know, how many kids you have. Kids you have. Okay. I cannot have 1.2 children. That's not logical, right? The reason why this is relevant then, do not connect the dots if it is discrete data. Let me say that one more time. Do not connect the dots if it's discrete data. Because whenever you connect the dots, what you're doing is you're assuming that all of those little points in between are valid. Does that make sense? That's what a connecting of the dots would mean. But if you connect the dots here, this means that in theory I could have 1.2 kids. That's not really logical. So if it's continuous data, you're allowed to draw a line through all of it. If it's not continuous data, you really shouldn't draw a line through it. Is that logical? Okay, so what I want to now do is function into basically the ideas of the ways that you draw functions, how you represent them. And I've kind of already done that a little bit so far. There are 4 main ways. The first one is I give you a table. And you guys have probably done this with quant, right? You do like an X, Y little grid here, and you plot a table of values. Ordered pairs kind of does the exact same thing. You can plot them on a graph. The last thing you can do is you can make an equation out of it. Before I get to the equation, let's just make sure you guys are comfortable with the other ones here. If I give you a 1, if I input 1, it gives you back 2. If I give you 2, it gives you back 3. If I give you 4, it gives you back 5. In a way, this is kind of a pattern. If I give you 5, anyone want to hazard a guess as to what it would give you back?
Yeah, 6.
What's the pattern?
Goes up by 1.
Goes up by 1. Now here's how I write this. My function, using x as a variable, is equal to whatever my number was, plus 1 more. You guys should have done this last year a little bit. This is a linear graph. Maybe you've heard like y equals mx plus b. Essentially, whatever you start with, your x value, your y value is 1 more. This value, 1 more. This value, 1 more. This value, 1 more. We can then start plotting some points here. So here's my first question. Is it fair for me to draw a line through these points?
No.
Why not? Maybe it's taking a step better. Could I use 1.5? Is there any logical reason I can't use 1.5? If I did use 1.5, it would give me back 2.5. What if I used 0.0001? Well, then it would give me 1.0001. If I use the number 17 million, well, then the next one would be 17 million and 1. is there really any number that we can't use? I'd say no, you can use whole numbers, decimal values. So it would be fair to draw a graph of this and put a straight line through it. And convention would be to draw an arrow to let us know that this keeps going for forever. Although the graph stops due to the limitation of the graph paper we use, this will keep going infinitely, won't it? If I can do 17 million and 17 million and 1, couldn't I do 18 million, 19 million? I mean, I wouldn't draw the graph that big, but wouldn't that logic still hold? You know, way, way, way up here, somewhere way up there, there's a point where it's 17 million, comma 17 million and 1. You know what I'm saying? It's loud. Right. Let's do a word problem. So here's a scenario. You go to a park somewhere, downtown Calgary or something. Only Calgary's way more expensive than this. Basically, the way it works is a flat rate of $10. And then after that, they make you pay $3 an hour. Can we represent this as a function and talk about then discrete continuous? So let's start with the first way I want you guys to be able to represent a function, a good old table of values. I'll just go x and y. So let's just start thinking this out one at a time here. Let's say that you park for 0 hours. So actually $10 because that's the flat rate, right? It costs you $10 just to get in. Okay. Now let's say you parked for 1 hour though. 13, right? Because, well, you add 3, right? And you don't need to make this table for forever. I'd say like 3 or 4 terms should be enough. So 2 hours is 16, 3 hours is 19. That should work. So that is one way of representing data in our table. The second way of doing it is to do ordered pairs. And honestly, the ordered pairs are the exact same thing. One of them is 0 with 10. Another one is 1 with 13. Another one is 2 with 16. And then 3 with 19. Honestly, like these two things here are like the exact same as each other. Right. The third way I would want you to represent a function now is using a graph. So when you do a graph, let me walk you through some of my expectations of a graph. Okay. When you graph something for me, usually you're going to make some sort of grid like this. And I don't need you to use a ruler, not in my math class. In my physics class, I have a little different expectation. But in my math class, just draw me a grid like this. And I don't even really need you to like put little hash marks along the edge there. I'm actually okay if you don't. Because I'm more worried about speed here than just, being nitty-gritty details. Then what I'm going to do is I'm going to kind of figure out like a range and a domain to go from. What's the lowest number I have right here in my x column? Okay, well, why don't I say that 0 should start right here? And then where's the biggest number in the column?
19.
No, in the x column. 3, okay. So maybe I'll make this 0, 1, 2. I'll just say that 3 is somewhere over here. I'm just kind of saying where the lowest to the highest values are. And then, I guess since I'm starting here at the origin at 0, 0, the highest y number is 19. Maybe what I'll do is I'll just make it go from 0 to 20. I'll just say something like that. What I want is just a little perspective as to whereabouts are we. We're going from 0 to 3 and 0 to 20. And then now I just want to plot approximately where they'd be. I don't need you to like make a nice grid or anything like that. I would say that, well, like 1 should be about here, 1 and 10 would be about there. But I want to use the word about. Don't worry about plotting it exactly there, because here's how I'm going to know where it is. I want you to actually say 0, 10. I want you to actually write that next to it so that I know that it's at 0, 10. And then, like, that's not where 0, 10 is, though, is it? 0, 10 should be right here. That's where 0, 10 would be. Does that make sense? Sorry if I screwed you with this. Well, but like it has to make logical sense, right? Like as to where it goes. Because then for the next one, 1 and 13, 1 should be about here, 13 should be about there. Again, don't take the time to like grab graph paper and to use a ruler. I mean, if you really want to, you can, but I don't need that. I just want to make sure you have a rough idea what this looks like in your head. Then 2 would be over here. 2 with 16 should be something like that. And then 3 and 19 should be something like that. If they're not perfect, don't sweat. One more thing here though. Should we put a line through this? Is this discrete or continuous data? Because the way they do it in the parking lot is they charge you for either 1 hour or for 2 hours or for 3 hours, but they don't really charge you for 4 hours and 32 minutes and 5 seconds. Right? So really, on this one here, we should not put a line through it because this was discrete data. You either park for 1 hour. If you park for like say 47 minutes, they charge you for an hour, right? If you park for like 2 hours and 1 minute, they'll probably charge you for 3 hours, right? Like they make it to the nearest number. I do want to talk about one more thing here though. The fourth way of doing this, we need an equation. So it'll look like this: f of x equals something. Now, last year you guys should have learned about y equals mx plus b. Right? Basically, you've got like a slope and a y-intercept. Maybe this rings some bells. But here's your equation. It's 3x plus 10. Maybe you remember this from last year. You start it with $10, and then every time you go up by an hour, you have to add 3 more. So this would be an equation that goes along with it. And all 4 of these things mean the same thing. A table, a bunch of points on a graph, and an equation all really refer to the same concept. Is this kind of familiar?
Yeah.
All right. So let me do some review of what you learned last year then for linear data. It's considered linear if it basically goes in a straight line. And I'm not going to review like all of grade 10 right this minute. Yeah. Oh. Okay. But normally what ends up happening is it's like this: y equals 3x plus 2, y equals 5x minus 4, y equals negative 2x plus 1. It always fits that kind of format where the number in front of the x is the slope value, and the last number, the constant term, is the y-intercept. Hopefully you kind of recall that concept. What happens if the slope is a negative number? Do you guys remember what that means? It goes downhill. Yeah, a negative slope would go downhill. Okay. So here's some more notes just referring to that whole function notation. If I give you the graph y equals 4x minus 2, you might see it written as f bracket x 4x minus 2. I want to talk about how to say this, because you're going to see this a lot. F bracket x, the way that you say it out loud is f of x. That's how you say this. Okay. So whenever I talk of f of x, that's what I'm referring to right here. I'm not going to say f bracket x close bracket. I'm going to say f of x. Basically, it means find me a function where x is your variable. So here's another example, kind of just illustrating what I've been talking about. I could give you an equation. I could give you a table of values. You could probably plot it. But my goal right now is not to recover grade 10. It's just to remind you of some of the terminology that we use and some of the concepts behind graphing. So, do you guys feel like this is relatively familiar?
Yeah.
Okay, we'll move on. So now what I want to do is talk about how to use your graphing calculator. So I really hope you have one. That will make your life easier. If you don't, I really mean this. You absolutely need one. You cannot get by without one. Okay. Beg, borrow, steal, barter. I think Noni sometimes signs them out. Maybe don't steal actually, but borrow. Okay. If you do have a graphing calculator, I want to show you guys a whole bunch of the buttons involved in it. I need to start. This is driving me nuts. Okay, let me start by saying this, guys. If you ever have an error on your calculator, there are probably thousands of different error codes where if you ask your calculator to do something, like for example, if I want to try to square root -2, my calculator will give me like some sort of error code. You guys ever come across these before where it says error something?
Yeah.
Okay, well, you probably will. Okay. I need for you guys to be able to troubleshoot how your calculator works so that if you ever get an error like this, you know why it's not working. Because essentially your calculator is a big computer. And if you ask it to do something and it's struggling to do that, there's probably some sort of problem with the code you're putting in. So I want to show you a bunch of the buttons on your calculator. So let's start here. Up in the top left-hand corner, there's one called y equals. If you start there, this is a location where you can type in graphs you want to graph. Currently, based on the last time I did this, I even have some graphs in there. So I want to show you a few little tricks that you can have when working with this. First of all, if you want to get rid of the old ones, press clear. Okay. Another thought. There are as many as 10 graphs available. Okay. Once in a while, an error code may show up because someone typed in some random gibberish down here in the bottom. And then when you go up here and you try to type in a normal graph, like say negative 2x plus 1, and you try to graph it, I'll just press the graph button right now. See how it's trying to do something, and then all of a sudden it gives me error syntax? That's one of the first places you might have an issue, is make sure that in your y equals, that you don't have a graph sitting way down at the bottom here that makes no logical sense. Okay. So the first thing you should be able to do then is type in, say, negative 2x plus 1. Well, here's another button on your calculator I want you to be familiar with. You know how back here, when I had you guys draw this graph, I told you we went from 0 to 3 and 0 to 20, something like that? Okay. This window button right here allows you to change the scale of your graph. A normal, guys, make sure you give me your attention, okay? A normal default graph goes probably negative 10 to 10 and negative 10 to 10. But let me show you some reasons why, again, you might get an error code. If you try to go from, say, 20 to 10, your calculator won't be able to do this. Because if you ask it to find the minimum value of 20 and a maximum value of 10, and you try to graph, see how now I get an error code saying, I can't handle the window range because it's gone, like it's in the backwards order, right? So normally you want to go from like say negative 10 to 10, but it could be something like say 0 to 10 and 0 to 50. That'll work. In terms of other buttons on here that matter, let's give us X scale right here. Normally it makes sense to have it go up by ones, but if we're going from like say 0 to 50, maybe you want it to go up in groups of 5 or something like that. So basically this is the low to high number in X, and then how much it goes up by in terms of like how many increments it's going to put on the edges, and then the low and the high number in Y with the increments as well. For the life of me, I don't know what XRes means. I'm sorry. I don't actually know how it changes things. So, for right now though, can we, we'll just leave it like this. I want to show you another set of buttons. If, really quickly, you want to change your window back to a nice standard 10 by 10 window, the best way to do that is to press Zoom, and then go down to Z standard, a Zoom standard. This will make it a nice 10 by 10 window size. So even if my current window size is really screwed up, like this is my 0 to 10, my 0 to 50, and I don't even see a graph, if you go Zoom 6, it reverts it back to a nice 10 by 10 graph. There are some other nice little things you can do here, by the way. If you go Zoom in, for example, the second one here, if you want to get a closer peek at a certain location, see how I'm kind of moving the little cursor around here? Basically move it to where you want to zoom in and then press enter, and it will now zoom the graph in closer to where you want to see.
I'm guessing 0 out.
Exactly. Zoom out will then make it zoom outwards. Okay. Again though, it may be useful for you to then go back to a zoom standard just to go back to a 10 by 10 grid, because a 10 by 10 is a pretty normal size. Now here's some other buttons that are useful to you. Now these ones you have to press second before you get to that. So you gotta go second, table. See how table is hidden in there behind the word graph? This will give you a table of values. And as you scroll up and down, I mean basically you'll have exactly what I show you, right? I want to show you a couple of tricks on this though. Okay. Let's say that you want to figure out the y value when x is 1,000. Let me say that again. Let's say you want to find the y value when x is 1,000. I could keep scrolling down, until eventually x is 1,000. But isn't that ridiculous?
Yeah.
So I want to show you something else. It's called table set. And I don't know that you've seen this one before. Maybe you have. Table set is right there behind the window one. If you go second table set, it allows you to do two main things. The first one is it tells you where your table starts at. Well, if I want it to start at the number 1,000, I just type in 1,000. And if I go back to the table, hey look, now it's starting at 1,000, which is kind of nifty. This is also really useful then, because then rather than pressing the back button until you finally get it back to normal range, maybe that's a little ridiculous, go second table set and have it start back at 0 again. The other useful thing in your calculator is this little triangle, change in table. Most of the time, 9 times out of 10, I bet you want it to go up by 1s. But if you want it to go up by 5s, change that to a 5 and then go back to your table, see how now it's going up by 5s? So your table and your table set really go side by side. I do kind of know how the independent and dependent work here, but for the most part, you want to leave them both on auto. If you really want to know here, if you change it to, like, say, ask, what ends up happening when you go to the table here, you see how it kind of leaves the table blank? Now, if you ask it for x to be 1, it'll tell you what y is equal to, which is kind of nice in a way because you can just ask it for random values. The downside to it, though, is that sometimes it's just better just to have the whole table there for you anyways. So I don't see a lot of value to changing it from auto to ask, so I would leave it on auto. Okay. This is probably the most important button on your calculator. It's the calculate button. So it's behind trace. Go second, calculate. Calculate is what we're going to spend most of our time working with, regardless of -1 or -2. This is like one of the most important button combos on your calculator. Today I'm going to show you how to do value and zero if you haven't seen them already. And then later we're going to learn about how to do max, minimum, and intersect. The first 5 are the main ones we use. And if you eventually take calculus, I'll show you how these next 2 work in calculus. But that's when you're grade 12. So let's talk through how these work. If you press 1 for value, basically the way it works is it'll show up your graph again, and it's going to give you x equals a little blinking dot. And basically you then tell it, well, what do you want x to be? I want x to be 7. Oh, there you go. It's -13. That makes sense. Now, there's a few reasons why this might not work, though. If I try to ask it the value of x and x is 800, it's going to give me an error code. It's going to say it's invalid. So I want to talk about why there's an error code. Why was it available for me to type in x being 7, but not x being 800? My window's not that big. My window is set to go from -10 to 10. So if you try to ask it to find an x value outside the parameters, your calculator says I can't do that. So value is pretty useful. Find me the value when x is 7. There we go. It may not actually show up on the graph because -13 is way down here too low. But normally it'll put a little dot on there for you. Like if I want the value where x is 1, see how it kind of puts a little x right there for you, telling you where it is? Here's why this is useful. One of the things I'm going to ask you guys to do eventually is calculating y-intercept. Say that again. I'm going to ask you to calculate a y-intercept. The y-intercept is defined as when x is equal to 0. Let me say that again. The y-intercept is when x is equal to 0. So if I type in the second calculate the value when x is 0, that will find me a y-intercept right here on the line going straight from down.
That's way easier than the way we do.
That's the fastest way of finding a y-intercept. Second, calculate the value when x is 0. It'll find you any y-intercept. If you want to find an x-intercept, let me say this one more time. If the y-intercept is when x is 0, then the x-intercept is when y is 0. Now, sometimes you can find that by just going to your table and trying to see where y is equal to 0. Here's the problem. I don't see y being equal to 0 on here. But I'm sure it has to be, because if I go to the graph here, it definitely crosses right there. It just crosses on like an in-between value. So here's how we do this one. It's the second one down. It's called the zero. The way that one works. From here. So if you go to the zero function here,
I'll come right down.
here's how this one works. This is one where you have to narrow down a bit of a search radius for it. Okay. It's going to ask you for the left bound first. So what you want to do is you want to put this cursor somewhere to the left of where this x-intercept is, right about there. And right off the bat, I'd say it actually already is to the left. So what I can do is I can press enter and say, no, it's just to the left. Now I want to point out what happened here. Do you guys see how there's a little arrow right here pointing that way?
Yeah.
What your calculator is essentially doing is it's saying, I'm going to look for anything that way, which is an x-intercept. But it needs to define it a little bit better. It needs to also go on the right-hand side. So press the side-to-side arrows until clearly it's now on the other side of that intercept. And then press enter. And hopefully what you'll see here is that there's a second arrow kind of pointing inwards. Your calculator will now find any intercept within that search parameter. However, it's not done yet though. It actually asks you to guess. Now, there's a really good reason why I want you to guess, but for right now you can just press enter and pass through the guess. And it should find you where your x-intercept is at 0.5. Here's another way I could have solved that. I could have gone to my window size, made my table go up by 0.5s, start at 0, and look on my graph and say, hey, look, I did find where y is equal to 0. Because it was going up by 0.5s to make that work. What we're going to start to work with now, though, is graphs that aren't linear. Where I might give you x squared minus 6x minus 9. Okay. I want to show you something here. If I were to ask you to find the x-intercept using the zero function, I'm going to put this guy way over here. I'm going to use the side-to-side function and scroll it way over, even through the bottom where I can't even see it. Back up over to the side over here. Should show up in a second. There we go. Okay, I'm going to look for any x-intercept between this bar right here and this bar right here. Here's why I need the guess function. What if there's more than one? Can you guys see how there's an x-intercept right here? And there's an x-intercept right here? In case there is more than one answer, that's why there's a guess function. Because what you do is you put the cursor closer to whichever one you want it to be. And so currently, my cursor is right about here. If I now press enter, it will find me that x-intercept. But if when I press enter on the guess function it was closer to there, it might find me the other one. So that's why there's a guess function. You have to make sure that you don't forget to press enter through that. Because if you just do the 0 here, and you try putting it on the left, try putting it on the right, and then you say the x-intercept is 7.87. That's not right. My x-intercept isn't at 7.87, it is 7.24. So don't forget to press enter that one last time. Have you guys seen those before? Okay. Let me show you some more tricks. Let's say that you want to type in a graph, like this one right here, but you want to get rid of it for a while. You just don't want to retype it all. Like, you don't want to use it because you've got another graph you want to do. The next equation is x squared plus 6x. And then you have another one where eventually you learn how to do a logarithm of 2x minus 6. You'll eventually get to those. But let's say that you just don't want the first one. There's a nifty trick if you haven't seen it. If you can put your cursor on top of the equal sign and press enter, see how it's no longer blackened? You don't have to delete the equation out of your calculator. It will just now stop graphing it. Does that make sense? If I don't want to use this logarithm graph here because I'm not ready to try it yet, if I put the little cursor on top of it, it will now get rid of it, and now it should only graph me the other graph that's sitting there. So that's a nifty trick so you can keep the data in your calculator, but only use the one you want at a time. Eventually, you may even want to have two graphs at the same time. For example, let's say you want to have this logarithm graph as well. You guys don't even know what a log graph looks like, but that's fine. We're just going to go with it. But let's say you're not sure which one is which. There's also a way to figure that out. If you have a fancy new calculator, it actually graphs in color. But unless you have one of those, you have one of those? Or just do color? Yeah. Okay. But if you don't have one of those, if you go back, you see how there's this little line sitting right here? If you can go backwards with the arrow here and then press enter once, see how it's now flashing on a thicker line? Well, now when I press my graph button, it'll graph one of them normal, and it'll graph another one with a thicker line instead. That way I can tell which one is which. Let me show you that again. If you go back over to here and press enter, it can change the type of line it does. It actually has a lot of different options. This one here will actually shade half of the graph. So it's kind of like shading it in right there. If you're in my Dash 1 class, we're actually going to learn that later. If you keep pressing this button, you can actually shade the lower half of the graph. So I can kind of like shade some stuff in there. It's kind of cool. I would say 9 times out of 10 though, you just want it to be back on the good old-fashioned regular line one. There's even a dotted line one. So these are some nifty tricks for how to put graphs in your calculator. Use the equal sign and press enter. A lot of times I'll have kids, they'll have an error on their calculator. They'll say, Chris, why can't I see my graph? And they'll just say, I press graph, and I don't see something there.
It's not big enough.
Well, okay, so there's a couple of reasons. The first thing I'm going to check is I'm going to go right here and make sure that actually your equal signs are highlighted. Because if your equal signs aren't highlighted, you didn't tell your calculator to graph something. So let's say you did that. But it's entirely possible that your window size is set to something ridiculous, like say from 20 to 30, and from negative 20 to negative 10. If I graph this thing now, I don't see anything, right? And the reason why is that my graph is actually like say up over here, and I'm looking for it right there, and there's literally nothing there. Okay. So that will be the next thing I'm going to ask you to look at is what's your graph window size. For another hint, if you go to Zoom and you go down on Zoom to the number 0, Zoom Fit. If you're ever absolutely stumped, go to Zoom Fit. Most of the time,
It's awesome.
it will actually find a way to make your graph work for you.
It won't fit for you.
It will fit for you. Zoom Fit. Sometimes when you use Zoom Fit, you still want to like change your window size afterwards. What I'm going to need from you guys then is when you draw me a graph, it's going to look like this. You're then going to tell me that you went from 20 to 30. See how right here it says it went from 20 to 30? I'm going to put 20 to 30 right here. We went from 271 up to 711.
7-Eleven.
And then you're going to just basically sketch a quick graph of what it looks like. And my basic requirements are, I want you to include a couple of points. So then I might go to my table of values and say that, well, okay, I need points between 20 and 30, right? This is not between 20 and 30, so maybe change my table to go starting at 20, going up by ones. And label me a couple of points. Here's a point. This could be 24 and 423. This could be a point of 26 and 511. Okay. That's my requirement for a graph. Tell me where the domain and range run from, and give me a couple of label points. Does that make sense so far? Okay. I need you guys to be familiar with your calculator and all the reasons why it gives you an error. Because there are so many reasons why your calculator could all of a sudden say I can't handle something. So be familiar with some of the main ones, and I'll try to help troubleshoot as we get there. So I just want to do one last example. I want to try to graph and try to figure out this equation here. So you guys good for one last example? We can take a break.
I'm good with one more. Yeah.
Okay, last one. So here's a word problem. Your summer tires have 60 millimeters of tread, but every month the amount of tread goes down by 0.77 millimeters.
Oh my.
Right? I mean, essentially what happens is your tires start with lots of good winter tread, and eventually they become bald, and then you need to buy new tires because you have no traction anymore, right? So here's the first thing I want us to do. Let's try to write an equation. So it's going to look something like this. F of x equals blank. What's our slope? What is it changing by every month? But not just 0.7, negative 0.7 because it's going down. So our slope is negative 0.7. What's our y-intercept? What's our initial starting value?
16.
Perfect. There you go. We got an equation. So here's what I would expect you guys to be able to do then. Go to your calculator. And, I mean, maybe you don't want to get rid of the old equations. Honestly, if I give you a word of advice, get familiar with the idea of leaving the old ones in your calculator, because when you need help from me later, it sure saves time that you don't have to retype them all in again. Right? I mean, eventually you're going to run out of slots, right? But I'm going to go down to the fourth y and type in my graph of negative 0.7x plus 16. But I'm actually not going to press graph right away. You can, but if I press graph, my window settings make nothing show up. So before you press graph, you may want to go to your window and try to figure out what are some logical settings. Well, I'm going to start with Zoom Standard to begin with. Okay, I went to Zoom Standard, negative 10 to negative 10. And I actually have a little bit of a graph, but it's just right there in the corner. That's not really smart to try to graph it like this. That's not a good graph, right? So using some common sense, let's go to the window size and try to figure out what a good graph would be. And I might recommend, let's go from 0, because we can't go into the negatives, right? Let's go from 0 to something. Maybe from 0 to, I don't know, 50. And honestly, if this is too much or too little, I change it later. And then rather than going from negative 10 to 10, let's go from 0 to at least 16. How about 17? Because there's no point in going higher than 16, right? Now when I graph it, oh, there's a good graph. So here's my expectation for you guys for the graphing of the data. It would look like this. Draw me like an L graph. Guys, are you focusing? I know it's a long lesson, but you really should watch, okay? Tell me what your window size went from. Our window size went from 0 to 50, and from 0 to 17. Tell me what window size your calculator used. Then just draw me what the graph looked like. It looks roughly like that.
Exactly.
And give me a couple of points. I don't really care which ones you do, just give me a couple of them. So go to your table.
16 and 0.
Well, actually 16, according to my table, gives me 4.8. Or I could use, I don't know, 6 and 11.8. Honestly, guys, I don't care which point you use, just give me some. Does that make sense? Doesn't have to be on graph paper, doesn't have to involve a ruler, just to give you some points. If I were to ask for a table of values, there it is right there. Month 0, it's 16. Month 1, it's 15.3. Month 2, 14.6. You guys can probably keep going, right? Let's find the y-intercept. Well, the y-intercept based on the equation is 16, but let me prove it to you using the calculator. If I go second, calculate, the value when x is 0, when x is 0, you have a y-intercept. There, my y-intercept is
16.
16. There you go. So plot that on the graph. 0 goes with 16. I think you said one backwards, didn't you? You said 16, 0, didn't you? Make sure you don't flip the x and y.
Sorry.
That's all right. I didn't ask for this as one of my questions here, but a common thing I might ask you is what is the x-intercept? So here's how we find the x-intercept. I could go to my table and look for where it eventually reaches 0 in the y column.
Oh my goodness.
Shoot, it doesn't actually equal 0 in the y column. Well, I mean, obviously it did. It just equaled it on like a decimal number, right? So based on that, a smarter way of doing it is go second, calculate a 0. Okay. The way this works then is you have to go on the left and right hand sides of where your 0 happens to be. And sometimes the tricky part is knowing where your cursor is. Right now, I don't even see my cursor. It's currently at 0 and 16. So if I go to the left here, I finally find it. It's actually way up there. So I need to actually go to the right instead. There, now can you guys finally find where the cursor is? That's often one of the biggest struggles, is trying to find where your cursor is. And I'll say, here, this is good enough for right now. And then I gotta go way further. I'm gonna watch the y value. As soon as the y value starts getting into the negatives, that should be enough, because somewhere in here, down there, I can't even see it because the letters are in front of it, right? But somewhere in this little area right here, there is an x-intercept. But don't forget, guys, press enter through the guess, okay? Right, it is at 0 when it is 22.857 at 0. What does this mean right here? When are you going to run out of tread on your tires?
Halfway through.
Almost 23 months later. Right? Last question then. Continuous or discrete? This is continuous. Right? I mean, even look at this value here. Can you have a part of a tire tread amount? Does your tire tread always have to be either 1 or 2 or 3 millimeters? Not gonna be in between, right? Can you be partway through the month when you decide to look at how much treads on your tires? Sure. Right? This is most of the way, almost like this would be November of your 22nd, or it would be like, not November, it would be most of the way through your 22nd month. So it would be like day 27 or something like that of whatever month it is, right? Okay, does that make sense? You guys done that before? Yeah. So before we start doing actual quadratics, I need you guys to have some pretty comfortable words with the terminology we use, and you have to be fluent on your graphing calculator. Tomorrow is a fairly long lesson where we're not going to talk very specifically about quadratic graphs. Not to spoil too much, but the idea of a quadratic graph, when we get there, is it's going to have a unique shape. It's going to have this kind of U shape to it. So we're going to focus on that for a while. Dash 2s, that's as far as we go.
Yes.
Dash 1s, we will eventually then talk about other graphs like this one here. Linear, quadratic, absolute value, exponential, logarithmic, sinusoidal, cubic, tangential. There are so many graphs. But really, we do the exact same stuff. We find their domain, their range, their x-intercepts, their y-intercepts. So these skills, they really apply going forward. All right, questions, comments, concerns, that stuff? Okay, last point here. For the last couple of units, I've been making it so your assignments can kind of just be due whenever, willy-nilly. I'm going to go back to a little more of a structured schedule. So the first assignment is going to be due for everybody, regardless of which class you're in, this Thursday before you go. So if you haven't printed it off, print it off, and honestly, I would start on it. Okay, because I want to go back to structure. And a few of you are falling behind because I give you the flexibility to kind of do it whenever. And not everybody, but a few of you are like not done the first or second assignment. That's not good. So do Thursday, okay? And then you'll have another one due the next week.
What day is this day? Monday.
Sorry.